Yoav. Thanks to the organizers for having me here, and Happy New Year to everyone. This is joint work with Scott Commoners over at Harvard and Ron Schroer at Penn State, both economists. And we're going to start off by noting, as you all know, that there are finiteness assumptions baked into many core game theory results. For example, a lot of questions that you know, a lot of theorems that you know about equilibrium have finite sets of agents built into the theorem. A lot of stochastic games result have finite time horizons, maybe infinite time in one direction, but time starts usually at some point and doesn't start at minus infinity. Some theorems have finite data sets, theorems about rationalizing finite data sets. And, well, that's fine. And you could very well ask, in practice, everything is finite, either data that you're given or agents or time or whatever. And isn't infinity just abstract nonsense in terms of these theorems? And I'm here to tell you, first of all, that no, even if you only care about finite real world, you should care about whether your theorems extend to infinities or not. For example, theorems about finitely many agents, if you can extend them to infinitely many agents, they are more robust, and many times they're less susceptible to added frictions in more complex models, where theorems that only hold for finitely many agents but not for the limit would break if you add enough frictions. For finite time horizons, for example, if you have a theorem about time that starts from 0, and you can generalize it also to an infinite past horizon, it helps you distill the existence of dynamic steady states. If you're talking about finite data sets, there's for example, think about Afriyat's theorem that tells us, it's fine if you don't know it, that tells us that if you see finitely many points from a demand function, if you see finitely many the buyer with this budget and these prices chose this bundle, you see finitely many of these. Afriyat tells us that based on finitely many points, you cannot rule out the fact whether the utility function is concave or not. You cannot rule out whether it's continuous or not. Is this the case because Afriyat's theorem applies to finitely many data points? Or is this an inherent limitation in observing demand, that even if you had maybe all of the demand of the buyer at any given possible combination of budget and prices, you still could not rule these out? So all of these, even if you care about only finite real-world data, understanding whether these can be generalized to infinity or not would give you a lot of information, a lot of intuition about what's going on. And so it's not just abstract nonsense, but unfortunately, finiteness assumptions are incorporated into models not only for simplicity, but they play a real role in the analysis. And dropping finiteness usually translates into completely rewriting the finite case proof with added details. There's no general reduction from finite to infinite or from infinite to finite, and many times even not only rewriting the proof with more detail, but coming up with a completely new, even more elaborate proof. So for example, a lot of people here are familiar with Brouwer's theorem. That's the fixed point theorem that's used to prove Nash's Nash equilibrium existence. How many people here know Schauder's theorem by heart? Schauder's fixed point theorem? Well, that's the specific tool that Peleg used to generalize that for infinitely many agents in 1968. A lot of people here know how to prove the existence of stable matchings in finite markets. Gil Shapley's 1962 have a beautiful algorithm. I guess that more people here know Tarski's fixed point theorem, but still not as many as the people who know how to do the direct proof. So a lot of times for infinite markets, you have to, in the good case, rewrite the proof with heavier tools, and in the kind of worst case, find a completely new approach. And today we're going to talk about a unified, user-friendly, you'll see what I mean, approach for a generic infinite to finite reduction that will reprove these, but also do much more. So we're going to talk about the three cases that I talked about: infinitely many agents, infinite past horizon, and infinite observed data sets. In the first one, we're going to talk about stable matching, the setting without money, and Walrasian equilibrium and trading networks, that is setting with money. For infinite pasteurizing, we're going to talk about what's called dynamic stable matching with tenure. And for infinite observed data sets, we're going to talk about revealed preference theory. These are examples. We have other applications as well. So for each of these, for examples, there are canonical results for the finite cases. For two of these, namely stable matchings and revealed preference theory, there are also infinite versions of these theorems. So as we said, Fleiner has a existence of stable matchings in infinite markets via Tarski's theorem. So it's basically a completely new proof. And rationalizability of finite data sets, Afriat 67, a very, very seminal result, took basically 50 years for Phil Rennie and a fairly recent econometrica paper to reprove this for infinite data sets with a completely new elaborate proof. Nonetheless, there are open questions in all of these. You can ask, for example, okay, so we have existence of stable matchings in infinite markets. We even have min-optimal stable matchings. Is the min-optimal stable matching mechanism strategy proof? That's still an open question. One thing here that Ravi Jagadisan last year showed that the lone wolf theorem, whoever knows that it's a variant of the rural hospitals theorem, that's the theorem that's usually used to prove strategy proofness of the min-optimal stable mechanism. This does not hold with infinitely many agents. So it's not even clear whether this holds, but if it does, it needs a completely new approach. For Walrasian equilibrium and trading networks, as I said, Hatfield et al., JPE, fairly recent paper. They know how to prove existence of an equilibrium in finite networks. Infinite networks is open, and more than one of the authors told us, well, the proof is so delicate and complex, we wouldn't know where to begin to generalize it to infinite networks. So before I talk about dynamic stable matchings, let me just give you a general idea of what that is. So basically, it's very similar to stable matchings. We have a set of women, a set of men, a strict preference for each participant over the other side. And a matching chronology is basically matching over time. So it's a mapping from woman time pairs to men who are on the market at that time. What do I mean by that? Each man has an arrival and a departure time. Women are always there. And a matching chronology is stable subject to tenure if, first of all, men have tenure in the sense that a man's match can only improve during the time that he is in play. And apart from that, any blocking pair at time t may only exist due to tenure. So M and W may only block at time t if W retained her match from t minus 1. So that's a very natural generalization of stable matchings over time. This is inspired by a games paper by Pereira, 2013, who analyzes school teaching positions. And it's very easy to see if the set of times is the naturals. If time starts at 0, it's very easy to see how to adapt Gale-Shapley to give us a stable matching chronology. For t equals 1, just run Gale-Shapley normally between whoever's in the market. That gives you something stable for time 0. And then when you go from t to t minus 1, just promote the old matches of women to be their top choices. That would guarantee to you that if a man does not get the woman he was matched with, he's going to get someone he prefers. That's it. You can do this by induction. What's really unclear here is what to do if there is no minimum time. If you don't have time starting from 0 or from minus 100 or from minus 200, say that there are men with arbitrarily early negative starting times, what can you do? One thing that you cannot do is solve backward from t equals 0. You can't solve backward from any fixed time points. And even there's no reasonable concept of min-optimal matching chronology, so it seems very unlikely that any
Gale-Shapley style proof is going to work. So this is a real challenge here. And for revealed preferences, as I said, Phil Rennie has a beautiful paper where he generalizes Afriyat's theorem to infinite data sets. But there is a whole literature on rationalizability and revealed preference theory in various contexts. And each of the papers there seems to use a completely different proof, to the point that you can find sets of 2 papers by the same 3 authors in the same very close time proximity with completely different proof. So it's not just personal styles. Really, a proof for one of these settings does not translate to the other. So basically what you would want is have some way of lifting these without reproving every one of them. And in the rest of this talk, I'm basically going to tell you how to do everything that's in this slide, using one principled approach. Before we go on, do you know who this is? This is Buzz Lightyear. His slogan is "To Infinity and Beyond." This is going to be important really soon. So, okay. Our hero today is going to be the compactness theorem of propositional logic. And I'm going to give you a crash course in Math Logic 101, propositional logic. So we start by defining a set of Boolean variables. For example, this is a weird example. You'll see soon why it makes sense. For example, let's say that I have a set X. I have 2 variables A and for each 2 elements A and B of X, I define a variable GT AB. You can define an arbitrary set of variables. Then the set of all well-formed propositional formulae is defined inductively. So the atomic formulae are your variables, GT, A, B, say, and then the negation of a formula is a formula. The disjunction of 2 formulae is a formula, the conjunction of 2 formulae and a formula, and so forth. And here are some examples. So obviously GTAB for some A and B. Or of 2 variables, not of the and of 2 variables, and of 2 variables imply another variable. All of these are kosher formulas. A word of caution, each formula is always finite. You have to be careful. If you end up by accident doing an infinite disjunction, everything's going to fall down. So there's going to be a real problem here. And for that, we're going to have my son Eshed here to remind us of that. You see how he's very careful with his big brother's Buzz Lightyear doll. I told you Buzz Lightyear is going to be important. We're going to need to be as careful with infinite formulas. So he's going to appear on the screen whenever there's danger of not being careful. So once we've defined a set of formulas, we can talk about a model. A model is a mapping from our variables to true or false values. Basically, maps from each value to either true or false. And the truth value of a formula in a model is defined inductively. For the atoms, it's whatever the model gives them. And then not phi is true if and only if phi is false in the model. Phi or psi in the model is true if and only if either phi or psi in the model is true. It's very, very straightforward. And here's our hero of the day. As I said, the compactness theorem for propositional logic. If you have a gigantic set of formulae and you want to find a model for it, this theorem says that there exists a model for a gigantic set of formulae if and only if every finite subset has a model. So if you give me a gigantic set of formulae and I need to prove to you that there's a model, I don't need to deal with the infinitely many formulae. It's enough for me to show you that for any finite subset that you give me, I can find a model for that. It's a beautiful theorem. And let's test drive it. Let's reprove a theorem in 2 slides that many econ students whine about in their bachelor's studies. So it's Spielrein's extension theorem. It says that if you have a set of any cardinality, any strict partial order on X can be extended to a total order. Usually this is proven using Zorn's lemma. Has anyone here ever managed to explain Zorn's lemma to a class of undergrads and feel like they're really following you? I share that sentiment. So we're going to do this in 3 lines using the compactness theorem instead. So give me a set X of any cardinality. I'm going to define these variables. Basically, for any A and B in the set, I'm going to define a variable that's going to tell me is A going to be greater than B in the total order that we're going to construct that extends the partial order that you gave me. And then we're going to add all of these formulae to our set of formulae that we're constructing. It basically says for any A and B, either A is greater than B or B is greater than A, but not both. And if A is greater than B and B is greater than C, then A is greater than C. Any model that satisfies all of these formulae for any possible A, B, and C corresponds to a total order on X. Since we want an extension of the partial order that we were given, we're going to add GTAB for any A that we're told it must be greater than B. If that's part of our partial order, we're going to add this as well. That's it. Any model for this is a total order that extends the partial order that we were given. Now, by compactness, I don't have to show you that there's a model for the infinite set. I have to show you that there's a model for any finite subset. How do I do that? A finite subset of these formulae mentions only finitely many elements of X. We know, and it's very easy to prove, that for a finite X, any partial order can be extended to a total order, QED, done. That's much easier than Zorn's lemma. We actually don't know that this proof was written anywhere. Okay, let's test drive compactness to prove the existence of a stable matching. Let's reprove Gale-Shapley, no algorithm. So just to be concrete, we have a set of women W, a set of men M. And matching is going to be a one-to-one matching between a subset of the women and a subset of the men. A pair blocks it, a pair WM. If each of them prefers the other to the match that they were given, it's stable if it's not blocked. Note that this is, W and M will be of infinite cardinality, but this is not a continuum approximation model. Each agent here is non-negligible. You can think about countably many agents. This is not the kind of thing where measure zero of agents do not matter or something like that. It's far more closer to a limit of finite models than that. And Gale-Shapley 62 tells us that if the market is finite, a matching exists, and we're gonna use this area to prove this for infinite markets. So our variables are gonna be match WM for any W and M. It's obviously going to mean in the matching that we will form that it's going to be stable whether W and M are matched. So first thing, if M is matched with W, it's not matched with any other W prime. Also, if M is matched with W, then W is not matched with any other M prime. If W and M, if one of them did not rank the other, then we're going to add that they're not matched to each other. At this point, let me go back and tell you how the preferences are specified just to be concrete. So each man specifies his first choice woman, second choice woman, third choice woman, etc. for any natural number. So it's an infinite list. Same for the women. And the formula that's gonna show us, that's gonna mandate stability is as follows. If M and W are not matched, either M is matched to some woman he prefers to W, or W is matched to some man she prefers to M. Let's look at this very closely, and Eshed is here to remind us that we need to make sure that this is not an infinite disjunction, and indeed say that this is for a specific M and W. M ranks W somewhere, maybe at place 1,000,003. So there are only 1,000,002 women he prefers over W. So this disjunction is going to be finite, and same here. So we're in business. All the formulae are finite. Any model for this corresponds to a stable matching. How will I show you that such exists? Logical compactness. It's enough for me to show you that any finite subset has a model, but any finite subset mentions only finitely many men and finitely many women. By Gale and Shapley, there is a stable matching in the market that's induced on them, and therefore any finite subset has a model. Therefore, the entire set of formulae has a model. We have just reproven that a stable matching exists in an infinite market. And you can also tweak this. I'm not going to show this to you today, to show that there's actually an optimal stable matching even in infinite markets. This is kind of a second order result because our proof that there exists a stable matching, you can think about that as a first order result. And even though that's not constructive, we can prove that there exists a stable matching that each man prefers to any other stable matching.
So here you're assuming that the preferences of each man and each woman is 1, 2, 3, 4, 5.
It's order omega.
It's order omega.
Yeah, I assume that.
Complete that completely.
No, you can actually Fleiner proves that for any order type. Here, this is a limitation of our proof technique. For this formula to be finite, we need this. Yeah, but yeah. So in cases that I'll show you soon, actually the things that are imposed on us by finiteness of the formulae, we actually found counterexamples otherwise. So it actually helped us flush out counterexamples. This is a different case. Okay, what about strategy proofness? So Dubins and Friedman, 81, Roth, 82, prove that the min-optimal stable mechanism is strategy proof. We have non-constructively shown that there is a min-optimal stable matching even in an infinite market. We can define the min-optimal stable mechanism for any given set of preferences, return that matching. We don't have an algorithmic definition for that mechanism, but it's nonetheless well defined. You can ask, is it strategy proof? Can any man manipulate it? And the problem is, first of all, as I said, existence of the min-optimal stable matching is not constructive. There's not an algorithm that you can follow. Note that the fact that something is strategy proof is not an existence result. Compactness is very useful in proving that things exist because you map models to things. If a model exists, these things exist. And second, if the existence of min-optimal stable matching was a second order result, this is at least a third order result because it talks about functions from preferences to the min-optimal stable matching. Nonetheless, we have a very concise proof. I'm missing 4 minutes to go over this proof, but it's very concise. And this completely proves what was not known till now, that in infinite markets, the min-optimal stable mechanism still is strategy proof. I'm going to just tell you one thing, that here we have to do something far more delicate than just brutally restrict to the sub-market that contains all of the people in the subset of the formulae that we're given. We have to do something a little more delicate that we restrict to a market that depends on the semantics of the manipulation, even though it's a syntactic proof. So it's something delicate. And recall that I told you that the lone wolf theorem, that's the thing that's usually used to prove strategy proofness, does not work in infinite markets. So in fact, even though the main feeling of most of the people that we spoke to is lone wolf doesn't hold, why are you looking at strategy proofness? What we show here, in fact, that strategy proofness is a more salient feature of matching markets than the lone wolf theorem. It actually holds even in cases where lone wolf does not hold. So in fact, the lone wolf theorem is more brittle. So it's the other way around than what was commonly assumed. So we can reprove this, prove this. Dynamic stable matchings, you remember you've seen this slide before. So let me just tell you, by now, most of you will be able to figure out how to show that a dynamic stable matching exists even in an infinite past horizon. Write down formulae that say that something is a stable matching chronology. It's going to be very similar to what you've seen already. Give me a finite subset of these. There is a minimum time that is mentioned there. You can solve from that time as t equals 0 using induction. A model exists for the finite set, therefore also for the infinite set. And that's it. Compactness also shows that this exists from minus infinity. You need some condition here to guarantee that your formulae here are finite. As I told you before, when I'm asked here, this actually helped us flush out a counterexample otherwise. So this was completely the correct, whatever was forced on us by finiteness of the formulae was exactly the tight thing for a matching here to exist. Well-Raygian equilibrium, let me just say really fast, it's a canonical model. Here, the proof is going to be a bit more delicate. It's going to have price OP, meaning that the price of an object is P, and consumes AO, meaning that agent A consumes object O. And the problem here is that having a variable for each continuous price is problematic, because you're going to want to have an equation that says the price of O is either P or P1 or P2 or P3, et cetera, you can't have an infinite disjunction there. So that's one challenge. The way that we solved it, look at epsilon equilibria on a finite grid price. Then this equation is finite. You can, in any finite market, you get an equilibrium from the work of Hatfield et al., rounded to get an epsilon equilibrium. Therefore, there's an epsilon equilibrium in any finite market. So by compactness, there's an epsilon equilibrium overall. That's re epsilon. Take the limit of epsilon equilibria, you get a precise equilibrium. You can do that there. That not in every market whatsoever, under their assumptions that they need for the finite case anyway. Okay, good. Last thing I have. Sorry? 2-3 minutes. Perfect. I have one more slide. So, okay, revealed preference theory. Okay, so a data set D represents observations, and a single observation tells us our consumer, when faced with prices P and budget so-and-so, chooses bundle X. And the goal is to rationalize D via a utility function that's not degenerate. What do I mean rationalize? I mean that if you look at all of the bundles that you can consume with a given budget, given the prices, then the thing chosen in the observation really is a utility maximizer. And you want to do that using a utility function that's non-degenerate. Obviously, for a constant utility function, every bundle maximizes the utility, but the goal is to not use a degenerate utility function. Afriyat 67 gives us a sufficient and necessary condition for rationalizability. And more importantly for this talk, he tells us that if a set D is rationalizable, then it is also rationalizable by a continuous concave non-decreasing function that strictly increases when all coordinates increase. So he basically tells us if you only see finitely many samples, you can't rule out concavity. And this is basically the big win for all of the theorems in economics that say, let's assume that all the utility functions are concave. Afriyat tells us if you only care about utility functions corresponding to the demand that you've seen in practice, you can always assume concavity. What about infinite data sets? What if we're given every possible demand observation? What if we're given the entire demand function of the consumer? Is it still the case that we cannot rule out concavity? So Phil Rennie, as I said, beautiful econometrica paper, tells us that for infinite D, still the same condition for rationalizability, and without loss of generality, you can do that with a U that is quasi-concave, non-decreasing and strictly increases when all coordinates do. It's a new, elaborate, beautiful proof, and continuity or concavity cannot be guaranteed anymore. So continuity and concavity are artifacts of finiteness of the data set. Quasi-concavity are artifacts of the limitations of demand queries. That's the nice thing about generalizing to infinity. You can see what's an artifact of finiteness, what's an artifact of the way that you observe. And as I said, there are many, many papers on revealed preference theory, very diverse proofs, by and large, for finite data sets. Can we apply compactness to these? So once again, we have to be careful. Let me just point out that one challenge is that you need to rationalize using a strictly increasing utility function to avoid degeneracies. If you're going to try to discretize like we did with the Walleresian equilibrium and take a limit, you're going to lose strict inequalities. You may end up with flat functions. So that's one challenge. Nonetheless, we have a way to do this. We can reprove Rennie's result, and we can lift many other rationalizability results. Let's wrap up. Stay tuned. Actually, some of the things I told you about today are not in our archive version yet. This is really work in progress. There are more applications that I haven't told you about today that we're still fleshing out, so stay tuned for more applications. As we said, for finitely many agents, for example, even if you care only about finite markets, looking at infinity helped us understand that strategy proofness is more salient than the lone wolf theorem. Even if you only care about finite data sets, looking at infinite data sets helped us distinguish between properties that are without loss due to finiteness, and properties that are without loss due to looking only at demand queries. And logical compactness is a unified user-friendly approach for new and old results. Lets us reason about finite models in regular language instead of limiting processes and/or convergence. You don't need any obscure theorems, but you do need some creativity to get the formulae right. And the last sentence I'm going to say is that I kind of like to think about this in the context of the tradition of the 70s and 80s in game theory, where there was a lot of use of non-standard analysis to simplify a lot of proofs in game theory, notably in general equilibrium theory, most notably Anderson 78. So we're kind of very, it has nothing to do in common with the technicals, but morally we're kind of corresponding with that in the sense of bringing out tools from other branches of math in order to simplify results and reason with simpler semantics about problems that we care about. So thank you very much.
Take one or two questions.
Just a question about the unified approach. So you can think, of course, you gave Schauder and Brouwer as an example, but usually when you prove Schauder, you use Brouwer, right?
You use Brouwer, but you use Brouwer and steroids, yeah. Or you can prove it directly from separation theorems in analysis. Oh, okay. Okay, that's fair enough. We don't have a meta theorem that says if the finite theorem does ABC, then we can lift it without problem. With that, you're right. But it's a unified approach in the sense that I've shown you a list of 4 theorems, out of which 3 I don't think anyone would contest the fact that they're very canonical. Each one of them required many, many lines. Some of them we didn't know even how to reprove. And even the ones that we knew how to prove that involved a complete rewrite of the underlying finite proof, which was hard as well. And we can lift each of them without caring about how the finite result was proven. So it's conceptually it's a unified approach. I agree that we don't yet have a theorem that says these are the precise conditions under which we can lift results.
So that's came to my question. So maybe the advantage here that it's kind of topology free, it seems like.
It's topology free, even though obviously the compactness theorem it is a special case of Tikhonov's theorem if you look at it close enough. But it's a special, very user-friendly case of Tikhonov's theorem. Okay. Thank you.